Welcome again, DI504, Foundations of Deep Learning. Before we begin this week's lecture, let me talk about some administrative stuff. The previous week was the midterm. I'm working on them. I have two courses, I'm finished with the midterm of the other one. I've started working on yours. I mean, there are 5 questions and more than 20 people, so it's going to take some time, but I'm going to finish it and announce it soon, hopefully. Plus, after this week, we're going to have another lecture about the sequence models. And when we are finished with these 2 weeks lectures, your teaching assistant he's working on it now. He's going to provide you the second lab and your second assignment. And finally, about the projects, you have uploaded the projects. Thank you for that. We are working on them as well. And if we find something insufficient or wrong about the proposals, we're going to let you know. Okay, so in the meantime, if we are not saying something, you may assume that everything is okay. Okay, but if you have any questions about your proposal or projects, please do not hesitate to ask. Maybe we could do it by the end of the lecture as an office hour. Okay, so let me begin now. If you don't have any urgent questions, do you? You don't. Okay, but and one more thing. I saw Berna in the list because one of your friends, Berna, emailed me. She asked me, are there going to be any classroom lessons? The thing is, this is how it's going to work. I mean, since this is hybrid education, we don't have to, but the thing is, I come to the institute every day. I mean, I have a daughter who is going to the school here in the campus, so I come here every day, and I'm going to do the synchronous lectures either in the classroom or in my room. And I can do them both. If people come, even if 1 person arrives, I'm going to do it in the classroom because I'm okay with that. But if nobody arrives, when I come here, and if it's 9:40 and nobody arrives, sometimes I may move to my room. But if you arrive and you cannot find me there, I can come here as well. So please let me know if you want a classroom lecture, okay? If I'm not able to come for some reason to the institute, I'll definitely let you know before Wednesday. I'll say that I won't be able to come, so do not come to the classroom. I'll make that clear. If I didn't tell you anything, you may assume that I'm going to be in the institute and there could be a lecture in the classroom. Okay, enough of the administrative stuff. Please interrupt if you have any questions. DI504, Foundations of Deep Learning, and we're going to talk about sequence models this week. This is a very important subject, in my opinion, because this is another important title of AI, because not all data is fixed length. Some data is sequential. It is streaming data. I mean, when we say streaming, we say I'm not necessarily talking about the streaming type of data in the internet like video. It has a sequential dimension, whether it's time or I don't know, they could be different as well. We're going to talk about it. We'll call it the sequential dimension. So what we're going to do is, we previously talked about feature spaces and score functions, the fundamentals of machine learning. Then we jumped to artificial neural networks and to convolutional neural networks, which were all about processing fixed size data. So image was fixed size, for example. But now we're going to talk about different type of models, which can get different varying lengths of data and which has a sort of memory, actually. We're going to talk about these concepts. So to understand sequence modeling, I think one should first understand the meaning of a sequence. And by the way, these slides are taken from my advanced deep learning course, the other course. There's another course I'm lecturing this semester. Some of you know this, sequence models in multimedia, which is an advanced level deep learning course. I mean, you should take an introductory level deep learning course to get that course. And these slides are taken from the first week of that course. So the introductory level to that lecture is kind of, I've summarized it here. So if you're interested in the subject, you should definitely take that course as well. Let me get back to the slides. To understand sequence modeling, first you should understand what is a sequence, and before that, what is not a sequence. Now, maybe it's best we give an example. Consider the problem of predicting the health risk of a person based on multiple parameters, readings, lab results, whatever. So you're trying to model a relationship between the readings, the reports, the, I don't know, the data to the status of the patient, which is a direct relationship if you understand what I'm trying to say. And in that direct relationship, the important thing is, when you model it using the conventional machine learning methods like feed-forward neural networks are, for example, artificial neural networks or CNNs are called feed-forward neural networks because there's no recurrent relation. What is a recurrent relation? We're going to see today, don't worry. In these type of systems, this one data point, one data vector, let me say, one patient's results, and the relation between those data points to that patient's status, if it is healthy, if he's healthy or not, is independent of another data vector. So I have a machine, I input some parameters of a patient, and the machine tells me he's sick. Okay, this relationship is independent of a relationship of another patient. I mean, it makes sense, right? Because that's another patient, you would say. But not all types of data is like this in nature. So the type of data we've seen before was a type of data where when we evaluate those samples, we have assumed that each sample is independent of each other. And in many problems, this is the case. In almost all convolutional neural network problems, this was the case. For example, AlexNet. You know AlexNet now. You feed a cat image and it tells you that it's a cat image. If you feed another cat image, it would behave like you have never fed something to it beforehand, and it would again say cat image. This is feed-forward neural networks, and CNNs and ANNs are feed-forward neural networks. They don't have a memory. They don't remember how many times you've asked the network if it was a cat image or dog image. It doesn't save anything in its memory. It's memoryless, okay? So the type of data that these memoryless models process are not sequences. Sequences are type of data where in the sequential dimension, you have some sort of notion of memory. And what is a sequence? We'll get there. We are trying to understand what is not a sequence first. So to understand what is not a sequence, I'm going to give some examples about I'm going to give you some real-world examples. For example, in artificial intelligence, the field of artificial intelligence, it's always a good practice to ask, to compare any type of model to human intelligence. So let's say, is human intelligence a feed-forward neural network type of intelligence, like a memoryless one? Let's see. So just like we ask a convolutional neural network, is this a cat image? Let's ask a person, is this a cat image? Okay. The first time you ask that person, is this a cat image? They would answer yes. They would say, it is a cat image. The first one, the first time you ask it. So this behavior is like an FNN. However, the way we perceive reality and process data is not like an FNN. Because if you ask the same image to a convolutional neural network, they would always give you the same answer. However, if you ask this question to a person, it would get weird. I mean, the second time you ask it, they would somehow change, most probably change their answer. Like, it's again a cat image, they would say. If you ask it third time, fourth time, fifth time, it's going to get funny. They would think that you are making a joke because they have a memory of the previous questions they asked. So what I'm trying to say is, although the cat images you've shown to that person are independent in nature, the way the human intelligence process that information is not independent. I mean, if you are the person who are asking the cat image, you're showing the cat images to that person, you wouldn't say, well, this cat image is independent from this cat image, so why are you acting weird? Well, that wouldn't make sense. I'm acting weird because you're asking me the same thing. Tell me why, kind of. So this is a type of sequence modeling behavior. We as humans tend to model the incoming data as sequences. We want to relate an incoming data point to the data point that came before it and before it. Okay, so that's sequence modeling. So if you know what a sequence model is, I mean, so we can behave as FNNs, fit for neural networks like CNNs, plus we have the ability to model sequences. Just like we say, give different answers. Well, we could say that we carry, to model this computationally, I would say that we carry states inside us. I use the word states deliberately because the notion of states in computational theory comes from the very early studies of artificial intelligence, and which relates to the fields of computer engineering that we know of, switching and automata theory, regular expressions, finite state automata. I don't know if any one of you have taken those courses. If you're coming from electrical or computer engineering background, you definitely did. But from other backgrounds, during the first years of computer engineering, like the Turing, Alan Turing, the field that Alan Turing was working on, the Turing machine, they are based on states. So when you're trying to design a type of intelligence, that type of intelligence is actually an automata, a state machine, which is, according to the input that it gets, it's switching between different states. So that's switching and automata theory and finite state automata. So our intelligence must have some sort of states inside us. Actually, states having those states, those finite or infinite states, we don't know how we are mathematically designed in theory, are actually a notion of memory. That's how we keep things in mind. So what makes us, how can I put it? What makes us superior to any feed-forward neural network is our ability to model sequences. And when we are doing that, we have states inside us. Hence, we can model history and we can process varying length data. Let's keep this in mind because we are going to apply this to different type of data. And we'll try to understand if it is a sequence or not. So in humans, unlike feed-forward neural networks, usually the incoming data is not independent of the data before them because that's how we try to perceive data. So that's a sequence, guys. A sequence can be thought of a list of elements with particular order, which means there is a dependency. We're going to use this word in sequence modeling a lot. There's a dependency between the words, between, not let me say words, in natural language processing it is words, but there's a dependency between the elements of the sequence. Good. So sequence modeling is a task of modeling what word, element, token, vector comes next. You are trying to model that because that's actual intelligence. Okay, that's one step ahead of CNNs. So a nice example is this, guys. I mean, this is the screenshots of a picture of a bird flying. So if you look at only this picture, you might, or this picture, the second one, you may have thought that the bird was gliding, not flipping its wings. However, with a sequence of images, we know that it's flipping its wings. So in order to differentiate gliding from flipping wings, you will need a sequence of elements. So to be able to solve certain types of problems, you definitely need sequences. This is a vision example, but it doesn't have to be. I mean, it could be any time series problem like stock markets. Or if we are going to give an example from health informatics, maybe in order to understand the state of a patient, maybe a single data point is not enough. Maybe we should just model and work on a sequence of data points that were gathered in some previous time intervals, like 1 month ago, 2 months ago, 3 months ago, for example. It could be applied to any type of field, any type of data where the definition of sequence applies, guys. Okay, so very basically, it was CNNs which told us that this is a bird, but it's going to be something something, not CNNs, which is going to tell us the bird is gliding, flying, or flipping its wings. And it won't be a CNN-only architecture, okay? So, because in this problem, we have history and varying length data. In this type of data, we don't know how many frames we have. So the length of the input is not fixed. However, any data we feed to a CNN must be fixed length. The input layer will accept some fixed length input, right? So the output is dependent on the previous input, and the length of the input is not fixed in one of the dimensions at least. I mean, I'm not changing the size of the image, but I'm changing the number of frames in the sequence of images. Okay, so this is definitely not from an FNN, not from a CNN. So what is that? I mean, the answer is obviously a recurrent neural network, RNN. That's where we are trying to get. But before that, we are trying to understand what a sequence is. So sequence models in general are not artificial neural networks. The first answer is recurrent neural networks, and that's what we are going to learn in these 2 weeks. However, the answer is not limited to RNNs. I mean, if you take that course, maybe not in this course, but if you take an advanced course on sequence modeling, you'll see that the type of models that process sequences are not necessarily recurrent models. There are advanced models like transformers, which are not recurrent in nature, but can handle sequences. But that's beyond the scope of this course. Okay, so let's continue the thought experiment about what is a sequence and what is not a sequence. So is image a sequence? Well, at first glance, we can say that it is not, because it is fixed length and it's a type of signal. And that's why convolutional neural networks, I mean, feed-forward type of neural networks are very good with them. Because usually, depending on the type of problem, an image is independent of another image. If they are dependent, sorry. If they are dependent, that's a video, not an image. So we can say they're an image, but actually, there will be cases in sequence modeling. We'll not handle those cases in this course, where images are also taken as sequences, but we're going to talk about it. I'm going to mention it, but again, beyond the scope of this course. Is video a sequence? Well, apparently yes. I mean, that's maybe the fundamental, basic example you can give. Image is not a sequence, video is a sequence, that's simple, because you can create varying length data and there's history. If you just swap the order of the frames, it won't make sense, it will be rubbish. So the order is important, there is dependency between frames, and it can be varying length. I mean, 2-minute catwalk or 1-minute catwalk, whatever. And depending on the sampling rate, the data length will also change, okay? However, what we can do is, because the first thing that comes to my mind is, can we handle videos with CNNs? Well, you can. What you can do is, you can get fixed length snippets from videos, like 3-second snippets. And with a sampling rate which is constant, you will have constant 3D data, like n by n times L, kind of. And feed it to 3-dimensional convolutional neural networks. What is a 3-dimensional convolutional neural network? In a 2-dimensional convolutional neural network, the filters are 2-dimensional, n by k by L. In a 3-dimensional convolutional neural network, the filters are 3-dimensional. I'm not talking about the depth. So yes, you can, and people do that. However, depending on the type of problem, again, if the thing you are trying to understand with that CNN, imagine you are trying to understand an action, if it is longer than that snippet, well, it won't work. So for some problems, yes, you can apply that fixed length idea to work with CNNs on video frames. Well, you may, but in the end, if it's a sophisticated and complicated job with videos, you will definitely need sequence models, because some actions takes 10 minutes, some actions takes 10 seconds. Good. So we are on that idea. Let's get to another type of signal. MMI people, you're familiar with this sound. Sound is a time-sampled amplitude signal. So it is definitely a sequence. So you convert the mechanical waves into electrical signals, and you sample them uniformly in time. You can sample a 10-second sound, you can sample a 20-second sound, doesn't matter. So in the end, whatever it is, human speech or music, sound is like a time series data. It's a time sampled amplitude data. It's definitely a sequence. I mean, if sound is not a sequence, nothing is. Again, you can handle sound by splitting it into fixed sized elements and work on them with CNNs. You can. And there could be, there could be cases that it will work for you. But in general, if you want to make sophisticated things with sound processing, you'll definitely need a sequence model to handle varying length data. Okay, is text a sequence? Yes, I mean, NLP people, the text is a sequence. A sentence is a sequence. It's varying length. You don't know how long will it take. And there is a strong dependency between the tokens, elements of a sentence, words. Model it that way. Okay, varying length and history. I mean, think about it as a translator, simultaneous translators. They're hearing the words, they stream it real time, and they're doing highly sophisticated sequence modeling job when you're doing this. From a sequence to another language sequence. They're called sequence-to-sequence models in sequence modeling, not beyond the scope of this course again. Okay, I'll get back to the question, is image a sequence? Well, actually, I mean, as CNNs work on them, they are not. Because CNNs work on images like scanning the image just from the left top pixel. They scan the image, I mean. They do a horizontal scan or a vertical scan, doesn't matter. They scan. But actually, we can handle images as non-sequential as well. Actually, humans handle images in a sequential manner. How do we understand images is actually a mechanism called attention in cognitive science. Attention is, when you look at an image, actually, we don't process it like computers. We don't just trace the pixels, the first pixel, the second pixel, third pixel. Let me just apply a max pool over it. Now I see. We don't do that. What we do is we detect parts and we jump over them. Actually, there's a process for that. Our eyes jump. If you've ever worked on cognitive science or attention, you know this stuff. When you look at an image, your eye makes a sudden jump movement. It just sees you, jumps and jumps and jumps. Actually, the order of these jumps are the way we understand the image. So by using these glimpses, we model the image as a sequence. And how many jumps you make will depend on your understanding of the visual world. So we have found a way, I mean, we did not, it's a natural way humans understand, a way to model images as sequences, right? So again, this is beyond the scope of this course, but even image can be modeled as a sequence. And if you model something as a sequence, believe me, you're doing a sophisticated job. Sorry. Okay, we continue. So what to do with the sequences then? So at least we know what a sequence and what is not a sequence right now. So we could talk about what to do with a sequence. Actually, you can apply any type of machine learning problem to the sequence. You could classify sequences, predict the next element of a sequence, transform a sequence, create another sequence, compare two sequences, and generate new sequences. I mean, generating a sequence will require another type of knowledge. Again, there are autoencoders, variational autoencoders. There are GANs, these generative adversarial models. We're not going to talk about them in this course, maybe introduce them as titles, but not in detail. So let me give you some examples. For example, sequence prediction. Sequence prediction is predicting the next element. It's like a sequence of words or characters in a text. A sequence of products bought by a customer. What is he going to buy next? We are trying to predict it. A sequence of events observed in logs. What is going to happen next? A sequence of frames in a video clip. What is the next element in the video clip? So it could be predicting the next value. It could be predicting the class label. It could be predicting the sequence. So depending on how you model the problem, actually, that's how you model the sequence as well. In these slides, I'm trying to give you a rough idea about how to model the problem definition for a sequence problem and how to model the sequence as well. So for example, what is the number? You've seen this in Facebook a lot of times. I mean, people love this. I don't know why. Trying to guess which number comes first. That's a sequence problem. So it could be single, it could be multiple. So if it is 1, 2, 3, 4, 5, the next one will be 6, kind of. Sequence prediction next value problem. Well, it is not like this. This example is meaningless, but if I told you predicting the next value of Bitcoin, well, it makes sense now because you're going to earn money. And most of the e-trading algorithms are next value prediction algorithms in sequence modeling. And another one is every time you write something on Google, actually Google keeps a sequence model just for you, actually an LSTM. We're going to talk about LSTMs. Just for you guys. You've been typing a lot of things on Google and Google keeps them. And in that model, it kind of trains a model with the things you have typed so far. So that's why when you write something, Google tries to predict the next words according to the things that you've written previously. So anytime you write something, Google makes simple training to update that model for you. So actually, try this. Star Wars sequel trilogy is bad was the first word I had because I think that way. Try it. It's not going to be the same for you. That's the beauty of Google. I mean, Google keeps a sequence model for everyone. That's why Google is the king. Okay, there are countless real-world examples. Or you could create a classification problem like AlexNet. I mean, a sequence comes. What type of a sequence is this? For example, an anomaly detection. It is a problem. Or another example in the slide, text sentiment classifier. So people write comments on internet. Is this a good type of a comment or a bad type of a comment? Do you want to classify them? You read the text and say it's a bad comment or a good comment. That's a difficult job. Or topic categorization. There are news. I mean, you want to classify news according to categories, food, sports, politics, whatever. Again, a sequence modeling problem because the input data is varying length and the dependencies between the elements of the sequence is very important in modeling the class that you're trying to find out. And anomaly detection, maybe one of the most important. There are sequences. It could be anything, guys. It could be a sequence of bank transactions that you want to find the anomaly, or it could be a power plant. The signals, the time signals, the currents, voltages coming into your system, and you're modeling that sequence to find an anomaly. It could be anything. Again, we work on these things on that advanced deep learning course I lecture. So if you take this course, I mean, but after you take this course, you will be eligible to take that course as well in the following semesters. Or another good example is the genetics, because chromosomes are varying length, and you feed them, you're trying to find a certain type of chromosome. Is that chromosome here, or classify them? In genomic research, they do this a lot. Okay, and health informatics, because usually health data is sequential. I mean, there are types of examples that we don't have sequential health informatics data, just like the one we have given in the initial slides, but usually it is sequential. So as people who are taking a course on data informatics, you may have realized at this point that most of the real world data is sequential. And most of the time, when we call a system intelligent, we're talking about the intelligent capacity of that thing, model, person, machine, its capacity to model sequences, because it is our capacity to handle sequences that makes us intelligent, actually. So whether it's health informatics or electronic trading or whatever, genomic research, medical informatics, doesn't matter. You need to be able to handle sequences. And in this course, we are going to have some introductory level tools to do that. Okay. So again, another problem is not predicting the next value, not classifying the sequence, but transforming the sequence into another sequence. They are called sequence-to-sequence problems. So you've got this, and you're trying to find out another sequence. I mean, these are not good examples, but for example, text is Google Translate is a sequence-to-sequence problem. And actually, these problems are quite new problems, guys. I mean, we had a very solid solution to machine translation in 2014 first. You'll remember that time. One day, Google Translate started working fantastic about 5-6 years ago. Because a group in Google published a paper, Sutskever, Vinyals, and Lee, they published a paper about sequence-to-sequence modeling. Again, these are advanced concepts of sequence modeling, which I cover in the other lecture, but we are going to see some introductory level business about these models as well. So, at this point, I think we've made a proper introduction to the subject. Now I'm going to continue with not the theoretical definitions, but how we can make this work mathematically. So this was the big picture. There was nothing theoretical or mathematical about it. We have made a theoretical definition of what is a sequence and what is not. What type of problems makes up a sequence problem, what types of problems are not sequence problems, and why sequence problems are superior and why they are important. That was the introduction to it. Now I'm going to take several steps back. I'm going to get to point 0, to the origin of it. How all sequence models started. So I'm going to make the first I'm going to talk about the first magical step that makes a feed-forward neural network a sequence. I'm going to add something magical to a feed-forward neural network, and it's going to be magically able to model sequences. And it's going to be a recurrent neural network. So we're going to talk about recursion. Okay. Before we talk, when we talk about recursion, actually, it's all about recurrent neural networks. Okay. And when we say recurrent neural network, we talk about a very simple type of recurrent neural network, what we usually call the vanilla RNN. You know, in English, when you say something vanilla, it is the most basic form of it. Okay. And to understand vanilla RNN, that magical step that makes FNN into an RNN, we are going to talk about a special mechanism, which is called the feedback mechanism. Before that, let's remember what was the artificial neural networks, the feed-forward neural networks. Guys, feed-forward neural network or artificial neural network, same thing. If there is no recurrent connection, which I'm going to talk about in a couple of minutes, is the thing that makes it recurrent. If there is no recurrent connection, the usual graph is feed-forward. So how will I understand what is feed-forward? If the input is always running forward in the computational graph, it is feed-forward. So what is the example that it could have run backwards? An example could be something like this. So, for example, so there's the input. So I calculate this, then I calculate this. If I did a calculation like this, sorry, like this, that would be a recurrent connection towards the back. However, we don't have this. This is not the case. So that's why it doesn't have any backward connection, which we call the recurrent connection, a feedback connection. It doesn't have these. That's why it is a feed-forward neural network. I hope everybody is okay with this definition of feed-forward neural network. Okay? In a feed-forward neural network, you already know this. We have nodes. The nodes have inputs from different nodes in the previous layer. If it is an input layer, from the vectors of the inputs. What it does inside is, you'll remember, it does a weighing, which means multiplying with the weights, plus summing up those weights and adding a bias and applying an activation. This was the node. I mean, it could be a convolutional neural network, another type of network. which we categorized as weight multiplication layers. Remember? So it could be a fully connected layer, artificial neural network entirely, or a convolution layer. This was what we've defined for neural networks, right? And it was taken from this idea of neurons. Okay, you already know this. And this actuation, which is nonlinear, gave the ability to the system the ability to model nonlinear surfaces in the feature hyperspace, the things that we have already talked about. So in an FNN, it's a simply connected weights in which you sum up the weighted actuations coming from the previous layer. So let me just clear my drawings. Okay. So, and you remember that these set of layers were called, these set of nodes were called layers. So the output of one layer will be the input to the other layer. And these layers are connected by some connections, which are actually the weights. So we combine many deep layers to construct deep neural networks. That was the idea, which is something you already know. Here comes the magic. This is a feed-forward neural network. If there's a connection from any of the nodes to its input, we call that a feedback connection or a recurrent connection, which is you sum these up, you have a value here. So the next time you calculate this, in addition to these inputs, this one, the output is also an input to that node. I mean, you have many questions at this point. I mean, it's not clear for you, I understand. Bear with me, but the fundamental question is, what is the first value? That's the initial value. That's, we usually said it's 0, but it doesn't matter. There's a feedback connection. It's a feed-forward neural network. It's a feedback network. When we have these feedback connections where the output of a node is fed to its input, which is called recurrency in mathematics, we call those types of networks recurrent neural networks. I know you have so many questions. I mean, when we do this, why there's, I mean, what we're going to just, in the end, we're going to say that recurrent neural networks are capable of handling memory or sequences. And how come? I mean, you have the right to ask that. Bear with me. It's a long journey to get there. But what I'm doing is, we've talked about sequences and we get to the very first starting point of sequence modeling, where we understand recurrent neural networks. So recurrent neural network is a type of network where there's a feedback connection. Okay, any questions about the feedback connection? Or up to now? Good. Please interrupt. So the feedback, we mean a connection from the output to the perceptron's own input. Okay, it makes sense. But what does it mean mathematically? Let's get there. Let's begin with the mathematics of FNN. I'm going to put the feed-forward neural network in matrix form. Don't worry, it's quite simple. It's simple linear algebra. So this is an input vector of length n. Okay. So I have the input vector, which is n by 1 here, right? I multiply, so I have n vectors, I have k nodes. So if this is a fully connected layer, let's assume it is, I have n times k connections, right? Which means I have n times k weights, because each connection is an indicator of a weight. We multiply them. So actually, I multiplied this guy with this weight, this guy with this weight, this guy, and I sum them up, right? So in linear algebra, actually, when you're doing the matrix multiplication, what you're doing is you are multiplying. So this is a weight matrix, which is k by n, which means there are n rows, and at each row, there are k elements. You're multiplying this k by n matrix with an x. So this is, sorry, this is n length. So this is, sorry, there are k rows, which is n length vectors, I should have said. You're multiplying this guy with this guy and summing them up when you're doing a matrix multiplication, right, in linear algebra. Same as you're multiplying each input with a weight. So this matrix multiplication can be defined as this weight multiplication. And this is something you already done in the midterm. So I don't think you have much problems about it. So, and we add the bias to that node, and we apply the activation function, and we obtain the outputs. And we do this for all outputs. If there are k nodes, there will be k outputs. So I could represent this feed-forward neural network with a simple activation function and a matrix multiplication plus the bias. That was what I did. Now, okay, simple, something we already knew. What about the RNN? In RNN, in addition to the FNN's connections, because we have the same connections, right? We have the same connections. So if we have the same connections, we will have these parts in mathematically as well. But we have something additional, this guy. And from now on, I'm not going to call the output Y, because in recurrent neural networks, the output of the recurrent nodes are called states. And states are usually denoted by A or H. Usually A, but H as well, because they are called hidden states. H as well. I'm going to denote them with A. So there's a recurrent connection as well. And that recurrent connection is the output state A itself. So how could I put it mathematically? So this is another layer which is not recurrent. It is not necessarily here, but I've added another layer to this. So there's a recurrent layer, there's a non-recurrent layer, and I've connected them. So the recurrent layer input is 1 by n. The recurrent layer's node size is k. So the output of the recurrent layer is k, 1 by k by 1. And I'm feeding that to another layer which has n nodes. So I can model this as A is calculated as a matrix multiplication between the x and w. However, these nodes take x as input and also take the A value as input as well. So I concatenate, combine the A vector with x here. I concatenate them. So this x was n by 1. So A is k by 1. So this vector is actually n plus k by 1. I concatenated them. So when I was concatenating them, I have taken the previous value of A. I mean, that we could call it the current value of A. I multiply it with these weights. As you can see, there are these connections, and there are these connections as well, themselves as well, because this guy is also connected to this guy, and like this as well. We have all these connections. That's why the number of connections I have is not k by n, but k by k plus n, because my new input vector is actually, when concatenated, k plus n. And I have the new A values. So using the previous A values, I'm obtaining the new A values. This is how I relate a dependency between the elements of a previous time to the next time. So I'm trying to create a mathematical meaning of state and history. Actually, it's going to work. I mean, it's going to work magically, but this is how it mathematically works. So A next is calculated from the A previous concatenated with X and a larger matrix here. Okay? So let me get to the other slide. At this point, we have two layers, the recurrent layer and the output layer. When we say the vanilla RNN, actually we are talking about only this part, because this is not the actual output. This is the actual output, I'm sorry. This is not the actual recurrent part. This is the feed-forward part. However, when we keep these as states, the hidden states of the system, by checking the hidden states and with an additional output layer, we get some predictions or classifications, whatever. I mean, you could create a score function here, and these could be fed to a softmax, and you could create a recurrent classifier where you feed different inputs. We're going to do those, don't worry. And this is the output. So it is a two-layered recurrent neural network where we have a recurrent layer and a fully connected layer. So what I'm going to do is, remember the formula of the core RNN. It was here, so I've written it more deliberately. So x is a varying length input. So at each time instant, an x vector, which is n by n, arise. The next n by n arise. The next n by n arise. Think of it as like images of a frame coming in. I concatenate them with the previous state, and I matrix multiply them. I can put this matrix in algebra into two separate parts. Like, so this is k times k by n matrix, k by n plus k by k matrix, two matrices. In this case, the formula of the RNN can be written separately as the feed-forward part, the feedback parts, plus the bias, which is the A next. I can do this. Okay? And I get A next to calculate the outputs. Okay. This is the actual input. It may seem that this is the input, but to this network, it is the actual input. Any questions? This is the vanilla RNN, guys. I mean, this is kind of a confusing diagram. I'm going to switch it to another representation in the next hour. But if you have any questions, please ask them. I guess not.